Welcome back, everyone. We've done great work practicing with our nomenclature rules and exploring what are aldehydes and ketones. Today's lesson will take a next step with the properties of aldehydes and ketones and looking at some chemical reactions that they are involved with. So physical properties and reactions today. Just to let you know, we're about, midway of page 6 in that printed note pack. These physical properties of aldehydes and ketones rely on the fact that they have very strong polarity. Remember how we drew earlier that our lesson showed that carbonyl carbon, based on its electronegativity difference, has a very polar bond, and it's giving a very region that's rich in electrons on top of the oxygen and a very electron deficient region on this carbon. We called this a polar functional group. It has a dipole moment. All of those to let us know that there's, I can spell and talk, that there is a region that's electron positive and electron deficient. So it's electron positive, very rich region up here, and electron deficient region here. So because they are polar, they have very high intermolecular attractions. They would exhibit not only dispersion forces, but they would also exhibit dipole-dipole interactions. They do not meet the criteria for hydrogen bonding as the alcohol functional group did. But nonetheless, they do have stronger intermolecular attractions than those boring old alkanes. So if you compare a 5-membered boring carbon chain, 1, 2, 3, 4, 5, as pentane, boiling point of about 36 degrees Celsius, put on a functional group of an aldehyde, and now that it has an exciting region, a polar region, the boiling point has increased. So the dipole-dipole interactions create a higher boiling point than a straight chain. It asks us to draw that interaction, and really it's just giving us an opportunity to discuss polarity. So if I were to draw, let's just take a ketone, for example, 3-membered chain. We'll put a ketone here. Remember that this is a very rich region of electrons. And so I'm going to just remind myself that's electron rich, so it's very negative. And here this carbon would be very deficient, so it's partially positive, that the dipole moment is pulling towards this oxygen. And you can then see that a neighboring molecule would have its carbon that's partially positive, kind of aligning itself so that it has an attraction between this and the next molecule. So opposites attract. That the oxygen, which is very electron rich on one of the molecules, is going to interact with the carbon on the next molecule. And so this attraction takes this negative oxygen and brings it close to the positive carbon center on the other molecule. That is, by definition, a dipole-dipole interaction. That intermolecular force, the intermolecular attraction based on the polarity of the bond. As we illustrate the relationship in boiling points, for the following molecules, let's compare a 5-carbon chain. So let's just draw pentane. 1, 2, 3, 4, 5. That's a pentane. C5H12. You can also just tell yourself, boring, straight chain hydrocarbon. Nothing really exciting going on there. Then we can draw in pentanal, which here that AL ending, or here it's asking for butanal, 4-carbon, 1, 2, 3, 4, and then you can see the double bond O. Here's the aldehyde. So this boring molecule has dispersion forces only. The aldehyde or ketone, a little more exciting, so it has dispersion forces and dipole-dipole interactions. But now remember from a couple chapters ago when we had alcohols, this is a very exciting functional group. So I would say medium exciting. Very exciting because an alcohol not only has dispersion forces, it has dipole-dipole based on polarity, and it has the strongest of strong intermolecular attractions called hydrogen bonds. So that's why we see an alcohol with the highest boiling point. It's the most exciting functional group, and the lowest boiling point is the most boring molecule with no functional groups, the pentane molecule. All are about equal molar mass. Highest boiling point, of course, would be the 1-butanol. It has the strongest intermolecular attractions. The lowest boiling point would give us the pentane, the most boring structure. Now let's compare, just based on molecular models, if we can predict which one of these would have compounds that would be higher or lower in boiling points. In letter A, I'm just going to pause the video just a quick moment. Hang on. All right, welcome back. I'm sorry to pause, but I just noticed we had a picture in there, and we're asked to being able to describe which one has the higher boiling point, and I don't have those pictures snapped into my notebook here. So I'm just going to draw what I see. Structure A versus structure B. I know I can see a CH3 group in the left leading to a CH2 group leading to a carbon double bonded to an oxygen. Then it's leading out to a CH2, leading out to a CH3. The molecule that's drawn there would be called 3-pentaneone. Let's compare that to letter B, which if I draw out, I have CH3 to the left, connected to CH2, connected to a CH2, connected to just a CH, down to a CH3, and then it terminates the chain. So this is a 1, 2, 3, 4, 5 carbon with a branch at carbon 3. All right, so I can clearly see that this is nothing but boring hydrocarbons, and that this is an exciting, not an alcohol exciting, so I'll put mildly exciting because it does have polarity, so this would have the higher boiling point. Letter A is your circled choice. Let's go down to the second choices, and we have C versus D down here. This looks like a 6-membered ring. And coming up off here, I have a ketone. Over on letter D, we have a 6-membered ring. And now up here is an alcohol. So as we said, this is mildly exciting. It is polar, but this functional group is very exciting because of the hydrogen bonding. And so this one would have the higher boiling point. Alrighty, so that allowed me to kind of just get processed. Thank you for letting me pause, draw these with you. And now let's go on and talk about solubility, another physical property. Aldehydes and ketones are always soluble in organic solvents. And it takes small molecules, just as we saw with alcohols and with ethers. These molecules that only have 6 carbons or less can also be water soluble. The molecules that are 7 carbons or longer, the non-polar region will dominate and they become insoluble in water. So you can see a 2-carbon, 3 carbons, 1, 2, 3 carbons. At carbon 2 is a ketone. So this very much is water soluble. But if I had 7 carbons or more, total carbons of 7 or more, then it would be insoluble in water. Acetone and progesterone are 2 ketones that occur naturally in the human body. Discuss their solubility properties of both compounds in water and in organic solvents. So this example was acetone given on the last slide, and we said that this would be water soluble. But notice this other one, progesterone. This is a very large complex molecule, and so therefore I'm not even going to bother drawing it, but you can see large number of carbons, certainly greater than 7, so this would be insoluble in water. Turning our attention to the reactions of aldehydes and ketones. Aldehydes can be oxidized. They are oxidized into carboxylic acids, COOH. I want you to make a note from chapter 14. We said specifically a primary alcohol can be oxidized, and that O just means oxidation, into an aldehyde. And it can be further oxidized into a carboxylic acid. I want to just remind ourselves what we knew from chapter 14 and carry it forward with us. A primary alcohol has attachments to 2 hydrogens and then an R group. So this is what we refer to as a primary alcohol. When this is oxidized, we remove a CH bond, and remember what happens when we remove one CH bond, it forms an aldehyde. So you remove one bond and turn it into a double bond, so here's what happened then. We had R, C, and then this turned into a double bond to create the aldehyde functional group. Now, all we're being reminded here in this new chapter is that if we start with an aldehyde, it also has an hydrogen. So see what happens here? This now is remove the CH bond and add back the COH bond. So now we have C still going out to the carbon, double bonded, and we add another oxygen there, and this by definition, see it, COOH, this is a carboxylic acid. So we know primary alcohols convert to aldehydes. Aldehydes convert to carboxylic acids. I am purposefully reviewing our primary alcohol lesson from before. And I can purposely review a secondary alcohol. Remember, a secondary alcohol only had one CH bond. So when it is oxidized, we removed one CH bond and turn it into a ketone, so that we had C double bond O, and then there was the other R. It turned into a ketone, and then it was done because we only had one CH bond to oxidize. And I remember learning that if we had a carbon attached to 3 other carbons, since there is no, this was what we called a secondary alcohol, a tertiary alcohol has no CH bonds, therefore no oxidation can occur. Now, that's review from chapter 14. Focusing on what aldehydes do. Aldehydes have one CH bond. Remove the CH bond and add an OH bond. So here you have COOH, our carboxylic acid functional group. Okay, great work there, trying to bring back some previous knowledge and tie it into the current knowledge. I better go check on that. Hang on. Okay, thanks. I just let the dogs out. So in oxidation, the aldehyde CH bond is converted into the carboxylic acid COOH. So the increase of carbon to oxygen, that's our very definition of oxidation, is increasing the number of C to oxygen bonds. Oxidation. It means to increase the number of C to O bonds, and that's exactly what we've done. We removed a CH and we added a carbon to oxygen, creating a COOH. Carboxylic acid is formed. Ketones cannot be oxidized because there are no carbon to hydrogen bonds. Notice that oxidation requires a carbon to hydrogen. And since a ketone is only connections to other carbons, no reaction occurs. And this is potassium dichromate, which is what we refer to as our oxidizing agent. So you may see potassium dichromate on the arrow, but oftentimes you see that just written with an O to stand for oxidizing agent. Let's show the oxidation of butanal with potassium dichromate. Butanal. So I have a 4 carbon, and at carbon number 1 is our aldehyde functional group. This is what we call butanal. The carbon to hydrogen bond is what's required for oxidation. So just making sure you see oxidation, removing a carbon to hydrogen and exchanging it into a carboxylic acid at the end. So we'll go back to show our 4 carbon chain. And at the end, we have a carboxylic acid functional group. We will learn that a carboxylic acid functional group, when we get that far, that carboxylic acid has a name, butaneoic acid. Oic acid is how we will name carboxylic acids. And it's always at the terminal end. The OH group makes it at the end of the chain, butanoic acid. Sitting on the arrow is your potassium dichromate, or you may see that just abbreviated as an oxidizing agent. They are exactly the same term. Aldehydes can be selectively oxidized with a reagent known as Tollen's reagent. Tollen's reagent is one that you should memorize. The Tollen's reagent involves silver. Ag2O is silver oxide in the presence of a very strong base, ammonium hydroxide. Alrighty, so I understand that aldehydes are oxidized with the Tollen's reagent, but other functional groups are not. So this guy right here is an alcohol. It will not be oxidized. It's a secondary alcohol. The carbon that's attached to the OH group is attached to 2 other carbons. And do you remember just a short time ago how I went through and talked to you about secondary alcohols can be oxidized into a ketone? That is a very valid reaction mechanism. But we can use a specialized reagent to selectively oxidize aldehydes only and leave the alcohols untouched. So the aldehyde converts into a carboxylic acid, but the alcohol did not react. Tollen's agent, if you see Tollen's agent on the arrow, or if you see silver oxide on the arrow, do not oxidize alcohols, only aldehydes. So one of the side chains here is that you can see pure silver comes out of the reaction. So you can see kind of a silver mirror, a plating of silver on whatever reaction vessel you used for your chemistry. So what product is formed when we take cyclohexane, and at carbon number 1 there is the alcohol group, and at carbon number 4 is the aldehyde group. Notice that the alcohol had precedence because it's an oxygen, higher priority. And then therefore, the aldehyde turned into a COO, but the alcohol remained the same. So let's practice. Each of these carbonyl compounds is going to be treated with potassium dichromate. The potassium dichromate is an oxidizing agent. Aldehydes turn into carboxylic acids. So here's my 6-membered ring. The carboxylic acid that forms will look like this. An aldehyde, which is this functional group, aldehyde, turns into a carboxylic acid because the criteria is met for oxidation. It has a CH bond. It must have a CH bond to be oxidized. Here we have a ketone. A ketone, because it has no carbon to hydrogen bond, will not be oxidized. Let's look at letter A. I have a 1, 2, 3 carbon chain. Carbon number 1 is an aldehyde. Sitting on the arrow is potassium dichromate. Can be abbreviated just simply using an O for oxidizing agent. An aldehyde does indeed have a CH bond right here, and that is the site of oxidation, turning my aldehyde into a carboxylic acid. Let's look at letter B. Here is a carbon with a carbonyl group, C double bond O, and on either side of it is an ethyl group. So this is 3-pentane-one. Up here, just to keep practicing naming, this would be propane-al. This would be propanoic acid. Carboxylic acids coming up next chapter. Alrighty, carboxylic acids. Anyway, we notice that this is a ketone, and therefore ketones have no CH bond, so therefore they do not have the ability to be oxidized, so no reaction. And in letter C, 1, 2, 3, 4, 5, 6, 7, 8 carbons long. 1, 2, 3, 4, 5, 6, 7, 8 carbons long. At carbon number 4, 5, 6, yep, I want to make sure I had 8 carbons. Carbon number 3, I see a methyl group. Between carbon 6 and 7, there's a double bond. I'll make sure that gets in there. There's also a methyl group coming off of 7. But I do notice right here, this is the aldehyde functional group. And at the aldehyde, we realize will turn into a COOH, C-O-O-H, a carboxylic acid. So simply turning the aldehyde into a COOH group at carbon number 1 and just redrawing the structure as you see it. That's practice with your oxidation of aldehydes. And don't worry if there's any other structures there like a double bond. It won't play a role in the equation. Now, what product is formed when treated with Tollen's reagent? Remember to think this is very selective to aldehydes only. So in letter A, 1, 2 carbons long, what product will form is still a 2-carbon, but now it's going to be a carboxylic acid, ethanoic acid. just to keep practicing. Here we had ethane-al, or acetaldehyde. Here we have a, right here, oh, see this guy? This is an alcohol, and this is an aldehyde. So this only selectively, only will it have the carboxylic acid form over here. And the alcohol stays the same. Alrighty, here's some more practice. Here we have, let's see, an aldehyde functional group. So we'd have CH3, CH2 taken 6 times, and then the aldehyde simply turns into a COOH, carboxylic acid. This is a ketone. Ketones cannot be oxidized. This is an aldehyde. Aldehydes are oxidized by Tollens agent into a carboxylic acid. And this is an alcohol, and we know that alcohols can be oxidized by, let's say, potassium dichromate, but they will not be oxidized by Tollens reagent. So no reaction for the alcohol. I want to compare this. It's very, very clear. Letter D, if I had this on my arrow, that's a 6-membered ring, and I put potassium dichromate, this secondary alcohol, excuse me, would indeed oxidize, it's a 6-membered ring, into a ketone. But the Tollens agent does not oxidize alcohols, therefore it remained in alcohol with Tollens reagent. If the reagent had given me potassium dichromate, it would oxidize the alcohol into a ketone. Now, reduction of aldehydes and ketones are the exact opposite of oxidation of aldehydes and ketones. To reduce, we decrease the number of carbon to oxygen bonds, and we increase the number of carbon to hydrogen bonds. They are opposites of each other. When you see H, hydrogen, sitting on top of an arrow, I want you to just consider this as a reducing agent, because we're increasing the number of hydrogen bonds. So keep in mind, oxidizing agents, and we've given you some examples of oxidizing agents, such as potassium dichromate, or we've given you a second oxidizing agent as Tollens reagent. Those are 2 examples of oxidizing reagents. The opposite of oxidizing is reduction. So the reducing agents that you typically see are molecular hydrogen with a catalyst of a metal, typically platinum or palladium, but some positive, very rich metal. So our text uses palladium, PD, but often you can use platinum as well, which is right on top of it on the periodic table. So we're adding hydrogen across that double bond. Aldehydes convert back into primary alcohols. Ketones convert back into secondary alcohols. Aldehydes have a hydrogen already at the end, right? And so aldehydes turn back to primary alcohols. This group here, this carbonyl carbon, converts back into a COH bond, and it becomes a primary alcohol. So just think about breaking this bond, and then you're adding back an oxygen to hydrogen bond right here. Here is a ketone. A ketone will take this and turn it back into a secondary alcohol. So this break that carbon to carbon double bond and turn it into a COH bond, making it a secondary alcohol. Aldehydes are reduced to primary alcohols. H stands for the reducing agent, typically hydrogen gas, in the presence of some precious metal like palladium, is commonly used as the agent. Here is the general pattern of a carbonyl converting into an alcohol, aldehydes into primaries, and ketones into secondary alcohols. And let's track this. Let's put on our page butanal being reduced by hydrogen and palladium metal. So I have a 4-carbon chain. At carbon 1 is an aldehyde. This is butanal. Sitting on the arrow is a reducing agent, hydrogen, and in the presence you would see that as just a catalyst of palladium. That's a reducing agent. Since this is an aldehyde, notice the functional group here of the carbonyl carbon. Change that into an alcohol and just redraw. 1, 2, 3, 4. At carbon number 1 is still that original hydrogen, and now leading up is to an OH group. The carbon receives a 4th bond as the other hydrogen, and you're adding on a hydrogen to the oxygen as well. And so here we have now 1-butanol, a primary alcohol. Aldehydes turn into primary alcohols. We turn the carbonyl carbon into an alcohol functional group where the oxygen gets one of the hydrogens in the diatomic element HH, and the other hydrogen goes to the carbon to satisfy its octet. There's an example of butanal being converted into 1-butanol, a primary alcohol. Ketones are reduced to secondary alcohols. Let's do an example where we take 2-butanone. So we see our general formula. Let's do one very specific. Here's an example where I have on carbon 2 a ketone functional group. You will have a reducing agent sitting on the arrow. The reducing agent typically is molecular hydrogen, H bonded to H, with a catalyst of some metal such as palladium. A ketone will convert into a secondary alcohol. Now what that means, we're going to add a hydrogen onto the oxygen. You add a hydrogen onto this carbon, and here's what we redraw. All single bonds. The original carbonyl double bond is now an alcohol, and this carbon here received the other hydrogen to complete its octet. So we had CH3, CH2, CH3, just to see that those remained the same. And then we just made the secondary alcohol known as 2-butanol. Here the OL ending for the alcohol functional group. 2-butanone was reduced into 2-butanol, a secondary alcohol. You should practice. I'm going to ask you to pause your video lesson and practice the reduction reactions using hydrogen in the presence of palladium. Practice these and come back when ready to check with me. Okay, welcome back. So we're going to say we're adding hydrogen and we're just using some palladium metal. You could also just see this as a catalyst sitting on the arrow. We know that aldehydes convert back into primary alcohols. And so the primary alcohol, The hydrogen receives onto the oxygen and onto the carbon. So this functional group, which is an aldehyde, converted back into a primary alcohol. And so let's just write that. Here's the aldehyde, and here's your primary alcohol. So that fourth bond, that hydrogen was still there. We added one more to complete its octet. Here we have a ketone, a six-membered ring, and the ketone turns into a secondary alcohol where this carbon is now leading out to the hydroxyl group. So here you had cyclohexane-one, and here you have cyclohexane-ol. Let me just emphasize what happened there, just redrawing that. This carbon that was in the double bond has two carbons. Even though it's not there, you know it's there. The fourth bond is a hydrogen. You increase the number of bonds to that, and out here, there is your two hydrogens from the reaction. So you create a secondary alcohol known as cyclohexane-ol. Here we have an aldehyde. Aldehydes convert back into primary alcohols. 1, 2, 3, 4 carbon chain. 1, 2, 3, 4 carbon chain. The fourth carbon leads to an alcohol, a primary alcohol. This would be called 1-butane-ol. Here, this would be butane-al. Here we have a ketone in letter B. 1, 2, 3, 4, 5. Down here was a methyl group that's untouched. The ketone turned into an alcohol. We would name that 3-methyl, just to see how that was numbered. And then it's cyclopentane-ol for the alcohol. And here you had 3-methyl, cyclopentane-one for the ketone. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. A ketone turns into an alcohol, a secondary alcohol called 2-butane-ol. And the initial reactant in letter C here would have been 2-butanone. You don't need the 2, you could argue, because there's no other position for a ketone to exist. And then right here is a aldehyde. The aldehyde turns into a ketone, into an alcohol. So I'm just going to redraw the aromatic ring, alternate my double single bonds. The carbon now is a primary alcohol. Woo, we're doing great work, aren't we? When we consider just kind of general considerations for this, I'm going to just check our time, and yeah, we're doing all right on time, 39 minutes for this. Perhaps I'll take a break here, give you a break as well, and record a next video. Come on back when ready.